Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 9, Geometric Constructions, Invariants. Section 87, Invariants of Linear and Quadratic Binary Forms. An expression of the form a1x1 plus a2x2 is called a linear binary form in the two variables x sub 1, x sub 2. The word linear refers to the degree in the variables, the word binary to the number 2 of the variables. A convenient notation for such a form is a sub x. The equation a sub x equals a1x1 plus a2x2 equals 0 defines a unique element a of a one-dimensional form in which a scale has been established, namely the element whose homogeneous coordinates are x sub 1, x sub 2 equals a sub 2, negative a sub 1. If b sub x equals b1x1 plus b2x2 is another linear binary form determining the element b, say, the question arises as to the condition under which the two elements, a and b, coincide. This condition is at once obtained as the vanishing of the determinant, delta, formed by the coefficients of the two forms, i.e., the elements a and b will coincide if and only if we have delta equal the determinant by column a1, b1, a2, b2 equals 0. Now suppose the two elements a and b are subjected to any projective transformation pi. X sub 1 equals alpha x sub 1 prime plus beta x sub 2 prime. X sub 2 is equal to gamma x sub 1 prime plus delta x sub 2 prime, where the determinant alpha, gamma, beta, delta is not equal to 0. The forms a sub x and b sub x will be transformed into two forms a sub x prime and b sub x prime respectively, which, when equated to 0, define the points a prime, b prime, into which the points a, b are transformed by pi. The coefficients of the forms a sub x prime, b sub x prime, in terms of those of a sub x, b sub x, are readily calculated as follows. a1x1 plus a2x2 equals a1 times the quantity alpha x1 prime plus beta x2 prime plus a2 times the quantity gamma x1 prime plus delta x2 prime, which is equal to the quantity alpha a1 plus gamma a2 times x1 prime plus the quantity beta a1 plus delta a2 times x2 prime, which gives a1 prime equal alpha a1 plus gamma a2. a2 prime equals beta a1 plus delta a2. Similarly, we find b1 prime equal to alpha b1 plus gamma b2, b2 prime equal beta b1 plus delta b2. Now it is clear that if the elements a, b coincide, so also will the new elements a prime, b prime coincide. If we have delta equal to 0, therefore we should have also delta prime equal to the determinant a1 prime, b1 prime, a2 prime, b2 prime equals 0. That this is the case is readily verified. We have delta prime equal to the determinant alpha a1 plus gamma a2, alpha b1 plus gamma b2, beta a1 plus delta a2, beta b1 plus delta b2, equal the determinant a1 b1, a2 b2 times the determinant alpha, gamma, beta, delta, by a well-known theorem in determinants. This relation may also be written delta prime equal the determinant alpha, gamma, beta, delta times the determinant delta. The determinant delta is then a function of the coefficients of the forms a sub x, b sub x, with the property that, if the two forms are subjected to a linear homogeneous transformation of the variables with non-vanishing determinant, the same function of the coefficients of the new forms is equal to the function of the coefficients of the old forms multiplied by an expression which is a function of the coefficients of the transformation only. Such a function of the coefficients of two forms is called a simultaneous invariant of the forms. Suppose now we form the product a sub x times b sub x of the two forms a sub x, b sub x. If multiplied out, this product is of the form a sub x squared equals a11 x sub 1 squared plus 2a12 x sub 1 x sub 2 plus a22 x sub 2 squared. Any such form is called a quadratic binary form. Under proposition K2, every such form may be factored into two linear factors, proper or improper, and hence any such form represents two elements, proper or improper, of a one-dimensional form. These two elements will coincide if and only if the discriminant d sub a equals a sub 1 2 squared minus a sub 1 1 times a sub 2 2 of the quadratic form vanishes. The condition d sub a equals 0 therefore expresses a property which is invariant under any projectivity. If, then, the form a sub x squared be subjected to a projective transformation, the discriminant d sub a prime of the new form a sub x prime must vanish whenever d sub a vanishes. There must accordingly be a relation of the form d sub a prime equal to k times d sub a. If a sub x squared be subjected to the transformation pi given above, the coefficients a11 prime, a12 prime, a22 prime of the new form a sub x prime are readily found to be a11 prime equal a11 times alpha squared plus 2a12 times alpha gamma plus a22 times gamma squared. A12 prime equals a11 times alpha beta plus a12 times the quantity alpha delta plus beta gamma plus a22 times gamma delta. A22 prime equals a11 beta squared plus 2a12 beta delta plus a22 delta squared. By actual computation, the reader may then verify the relation d sub a prime equals a12 prime squared minus a11 prime a22 prime equals the determinant alpha gamma beta delta squared times the quantity a12 squared minus a11 a22 equals the quantity alpha delta minus beta gamma squared times d sub a. The discriminant d sub a of a quadratic form a sub x squared is therefore called an invariant of the form. Suppose now we consider two binary forms. A sub x squared equals a11 times x sub 1 squared plus 2a12 x sub 1 x sub 2 plus a22 x sub 2 squared. B sub x squared equals b11 x sub 1 squared plus 2b12 x sub 1 x sub 2 plus b22 x sub 2 squared. Each of these under K2 represents a pair of points, proper or improper. Let us seek the condition that these two pairs be harmonic. This property is invariant under projective transformations. We may therefore expect the condition sought to be an invariant of the two forms. We know that if a sub 1, a sub 2 are the nonhomogeneous coordinates of the 2 points represented by a sub x squared equals 0, we have the relations a sub 1 times a sub 2 is equal to a22 divided by a11. A sub 1 plus a sub 2 is equal to negative 2a12 divided by a11. With similar relations for the nonhomogeneous coordinates of b sub 1, b sub 2 of the points represented by b sub x squared equals 0. The two pairs of points a sub 1, a sub 2, b sub 1, b sub 2 will be harmonic if we have Theorem 13, Corollary to Chapter 6. The quantity a1 minus b1 divided by the quantity a1 minus b2 times the quantity a2 minus b2 divided by the quantity a2 minus b1 equal to negative 1. This relation may readily be changed into the following: a1 a2 plus b1 b2 minus 1/2 the quantity a1 plus a2 times the quantity b1 plus b2 equals 0. which, on substituting from the relations just given, becomes d sub ab equal to a11 b22 plus a22 b11 minus 2 a12 b12 equals 0. This is the condition sought. If we form the same function of the coefficients of the two forms a sub x prime squared, b sub x prime squared, obtained from a sub x squared, b sub x squared, by subjecting them to the transformation pi, and substitute from equations 1, we obtain the relation d sub a prime b prime equal to the quantity alpha delta minus beta gamma squared times d sub ab. In the three examples of the invariants of binary forms thus far obtained, the function of the new coefficients was always equal to the function of the old coefficients multiplied by a power of the determinant of the transformation. This is a general theorem regarding invariants to which we shall refer again in section 90, when a formal definition of an invariant will be given. Before closing this section, however, let us consider briefly the cross ratio R of a sub 1, a sub 2, comma, b sub 1, b sub 2 of the two pairs of points represented by a sub x squared equals 0, b sub x squared equals 0. This cross ratio is entirely unchanged when the two forms are subjected to a projective transformation. If, therefore, this cross ratio be calculated in terms of the coefficients of the two forms, the resulting function of the coefficients must be exactly equal to the same function of the coefficients of the forms a sub x prime, b sub x prime. The power of the determinant referred to above is in this case 0. Such an invariant is called an absolute invariant. For purposes of distinction, the invariants, which when transformed are multiplied by a power not equal to 0 of the determinant of the transformation, are then called relative invariants. Exercises. 1. Show that the cross ratio R of A1, A2, B1, B2 referred to at the end of the last section is R of A1, A2, B1, B2 is equal to the quantity d sub AB plus 2 times the square root of d sub A, d sub B, all divided by the quantity d sub AB minus 2 times the square root of d sub A, d sub B, and hence show, by reference to preceding results, that it is indeed an absolute invariant. 2. Given three pairs of points defined by the three binary quadratic forms a sub x squared equals 0, b sub x squared equals 0, c sub x squared equals 0, show that the three will be in involution if we have the determinant a11, b11, c11, a12, b12, c12, a22, b22, c22 equals 0. Hence show that the above determinant is a simultaneous invariant of the three forms. Chiefly Exercise 13, page 230.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.